Welcome to day 3 of National Science Day, and in fact today is National Science Day, February 28th. We are so happy and excited to have all of you join us here today on this really wonderful day to celebrate all the sciences. I'll be handing over the mic now to Professor Srikanth Bhattacharya, Chairperson of the Outreach Committee of the Academy Trust, Indian Academy of Sciences. Over to you, Professor.
Good evening. The students assembled at the YouTube channel, and we apologize for the delay. It was inadvertent and because of a technical glitch. We're really sorry for that. I'll quickly recap the history of the Science Day. This is called the Science Day because on this day in 1928, C.V. Raman announced his discovery, which later came to be known as the Raman effect. And he got a Nobel Prize for that in 1930. In 1986, the Indian government decided that this should be the National Science Day for promotion of science, and that's exactly what we are doing over this week-long program, of which this is the third day. There's one last thing about it. There's a web series going on in Sony Live about which is called Rocket Boys. I strongly recommend that all of you see this. This shows C.V. Raman, it shows the Indian Institute of Science, which makes me very proud. I'm sitting at the Indian Institute of Science, and such great people as C.V. Raman, Homi Bhabha, and Vikram Sarabhai have put their footsteps in this campus. Okay, today we have a mathematics talk. As you can see from the title, it talks about prime numbers. Professor Kaneenika Sinha of Indian Institute of Science Education and Research, Pune, is an expert on numbers, and it's her passion to talk about prime numbers. She has done it many times, and today she will tell us about prime numbers. Professor Kaneenika Sinha did her Ph.D. in Queen's University, and then she was a postdoctoral fellow at a couple of places in Canada, including a heavenly place called Alberta, which is in the middle of Rockies. I have been there many times, and it's truly heavenly. So Kaneenika is with us today to tell us her journey with numbers and take us along. Over to you, Kaneenika.
Thank you very much, Professor Bhattacharya, for the very kind invitation to speak in this event and for the introduction. I would just like to mention that the place where I stayed in Alberta, in Edmonton, was not at all heavenly, although the Rocky Mountains were kind of far away from there. So when I finished at Alberta and came back to India, that felt like being back in heaven.
Okay.
Today. Okay, I guess it's visible, right?
Yes. Yes, it is.
Okay. So today I'm going to talk about prime numbers and how they help to keep secrets. So just a request before I start, especially to the student audience members who are watching, please keep your notebooks and a pen or pencil ready to do some calculations. And I'm not going to be very strict about it. You can use your calculator as well. But if you do some of the calculations as we go along, you will enjoy the talk a lot more. So like I said, I'm going to tell you about prime numbers and how they help to keep secrets. And from time to time, I'll ask you some questions. So those of you who are watching from YouTube, please do type in your replies. Okay. So I think this is something that everyone would know. Do you recognize this show? This is a very famous show on Indian television. It's called Kaun Banega Crorepati. This is, of course, Mr. Amitabh Bachchan, the host of the show. And this was a Children's Day special. So he's talking to a young 11-year-old student by the name of Tushit Nikose. And here is the question that Mr. Bachchan poses to Tushit. What is common between 2 3, 7, 11, and 13. Okay, so would people in the YouTube link, would you like to guess what is the answer to this? Okay, since you already know the title of this talk, I think you would immediately know that these are all prime numbers. And in fact, Tushit was so excited by this question that even before Mr. Bachchan spelled out all the options, he just yelled, yeah, they're all primes. And he had to, I think he had to be told to calm down, but he did confirm that this was his answer. These are all prime numbers. And for this answer, he won rupees 3,000 directly. And then Mr. Bachchan asked him to explain something about prime numbers. What are prime numbers? And Tushit defined prime numbers. So as you all know, prime numbers are those natural numbers other than 1, which are divisible only by 1 and itself. They don't have any proper factors. So then there was a discussion about what divisibility means and what factor means. And as a number theorist, I was absolutely stunned that such a nice discussion about numbers was going on. And then at some point, Mr. Bachchan said that he did not know anything about prime numbers, and this was all new to him. And all the audience members started laughing. Okay, but now why is this important? So Tushit went on to answer many more questions, and I believe that day he won rupees 6,40,000. So now this brings us to a question. How does Mr. Bachchan transfer the money to participants? Okay, now when the show started, I think the maximum amount you could win was 1 crore. But in the last year or so, they have also allowed the option of going up to 7 crores. So here are some options, and you tell me whether these are right or wrong. So option A, he keeps rupees 1 crore in the drawer, and based on how much the participant has won, he counts the appropriate amount and hands it over. Is this correct? Okay, I already see a lot of you are answering that, through some of you think it does it through checks or through banks. So obviously, this is a wrong answer. After all, we are living in modern times. We don't do this kind of stuff anymore. Okay, so the option B is he signs a check and hands it over. And some of you have indicated that indeed this is how he does it. Well, many years ago, this is how he used to do it. So more than, I think nearly 2 decades ago, or a little more than 2 decades ago, when I was a student, at that time, we used to see on the show, he would sign a check and hand it over. But as of today, even this method is outdated. So what does he do? He takes out this very fancy smartphone, or I think it's a tablet, and he magically transfers the amount to winner's bank account. And as he does it in his, his somber voice, he says in Hindi, which I will not try to copy because it's not easy to imitate Mr. Bachchan, but in English, it translates as, yes, I'm transferring the money to you using a quick, safe, and hassle-free way to transfer money. Now, quick, we understand, as soon as he transfers, the receiver has received it. Hassle-free, of course, he doesn't have to sign a check or keep money with him. But why is this method safe? Okay, what does it even mean to be safe? So in this context, it means that when he transfers the money to Tushit's, Tushit is too young to have a bank account, but his parents' bank account, he has to ensure, the bank has to ensure that the amount reaches the right parties. There's no third unscrupulous party in between who steals the money. Okay, so how does this method, why is this method a safe method? Okay, so this is what we are going to talk about today. The answer lies in the magic of prime numbers. It lies in a property of prime numbers that was discovered by a young lawyer who loved mathematics in France in 1640. So we'll start talking about prime numbers and very interesting history stretching over more than 2 millennia. And then we'll come to modern day applications. All right. So what are prime numbers? As we just discussed, a prime number is a natural number n greater than 1, which has no divisors other than 1 and n. Okay, so for example, 3 is a prime, 5 is a prime, 7 is a prime, right? Oh, I forgot 2. 2 is also a prime. So 2, 3, 5, 7. Okay, now you'll see I'm very nicely eliminating all the even numbers other than 2 because those are multiples of 2. They are not, 2 is a proper factor for them. Okay, 9, is 9 a prime number? It's not, because 9 is 3 times 3, but then 11 is a prime number, and so on and so forth. Okay, so I think in up to school level, most of you do learn the definition of prime numbers. And you may occasionally be given some exercise where you are given some interesting number and you are asked to derive all its prime factors. Okay, so at the heart of that question is an important fact about prime numbers. It is called the fundamental theorem of arithmetic. So what it says is that any natural number n greater than 1 can be uniquely factorized into a product of prime numbers, meaning either n is a prime or it can be written as a product of primes and prime powers. But it's important to know that this expansion, this partitioning into prime powers in a multiplicative sense is unique. This is called the fundamental theorem of arithmetic. Okay, I'm going to tell you more about it. Here are some examples. So 69, okay, this number 69 is not a prime. You know that it is equal to 3 times 23. And I will let you think for 5 seconds whether you can actually write out another factorization of 69 into prime numbers. Okay, can you find any other prime factors of 69? You can't. Okay, this is what the fundamental, in 69 is a small enough number for you to check it yourself, but the fundamental theorem of arithmetic tells you that the moment you have one factorization of a number into its prime powers or its prime factors, there is no other factorization other than just changing the order. 3 times 23 can also be written as 23 times 3, and so on. Now the number 27. Okay, this is 3 into 3 into 3, right? So 3 divides 27 and 3 is the only prime that divides 27. So when you take 3 cube, you get 27. And there is no other way to write 27 as a product of prime numbers or prime powers, right? So these are examples which demonstrate the fundamental theorem of arithmetic. But here is an important point, which I think at least those of you who have already started learning theorems and proofs would know, that examples do not prove a theorem. Theorem is something that tells you why a statement is always true, whereas examples are only particular examples of that theorem. Okay, another very remarkable fact is that there are infinitely many primes. The primes just never stop. As your numbers become larger and larger, between 1 and a number n, you will have primes, and the primes just don't stop. Okay, you can have primes which are as large as you like. You have primes greater than 100, you have primes greater than 1000, you have primes greater than 1,000,000, you have prime numbers that are greater than 10 million, and so on. So this is a very beautiful fact. And this is something probably that you will not, I'm not sure if it's taught in school, but typically in a first year college undergraduate course, this is a theorem that is proved. Okay, anyway, so these are some facts we are going to keep in mind. And now I want to talk a little bit about the history of these things that I just told you. Okay, so at this point, let me ask you the following question. Okay, do you know, all of you have your mathematics textbooks in school. Do you know the ancestor of all these textbooks? The ancestor, so to speak, of all our math textbooks, or at least the way in which math textbooks are written, goes all the way to 300 BCE. Okay, so more than 2,300 years ago. And here is our friend Euclid, about whom you have heard in other contexts, I'm sure. But one of his remarkable contributions was that around 300 BCE, he wrote a series of textbooks which he called the Elements. So what do these textbooks do? His volumes gave us systematic presentations of fundamental concepts in mathematics. And he gave it through with the help of precise definitions, theorems, and proofs. Okay, so the way we study mathematics today, the way our textbooks present mathematical concepts to us, follow the format in which Euclid wrote. Okay, so some of the facts that come out of his Elements is, first, any natural number n greater than 1 can be uniquely factorized into a product of prime powers. Okay, the fundamental theorem of arithmetic. But it is a very, very curious historical fact that Euclid does not actually state this in his works, although to a large extent it is attributed to him. But he states a smaller result which leads to this theorem. But this theorem as such, the fundamental theorem of arithmetic, was stated for the first time in the year 1801 by a person named Gauss. We'll learn more about Gauss very soon. Okay, but Euclid does state in his books that in one of the volumes that there are infinitely many primes. Okay, so as long as 2,300 years ago, people did have the knowledge of these two facts about primes. And if you think about it in a philosophical way, what it tells us is that if you think of prime numbers as blocks, building blocks, so prime numbers are building blocks for the entire set of numbers, and there are infinitely many types of blocks to choose from, right? Okay, so here is a picture from Wikipedia. So these are the original, these are the fragments of some copy of Euclid's Elements. They date to more than 2,000 years ago, and they were discovered I think, I don't know the exact history, but you can look at the Wikipedia page to learn more. But the second picture is also very interesting. Okay, this is the title page of the first English translation of Euclid's Elements in the year 1570. And if you look at the Elements, if you look at the title page carefully, just look at the English here, okay? Look at the spellings. If you wrote those spellings in your class today, your teacher will not be happy. But, language, everything is something that evolves over thousands and thousands of years. So in 1570, when this was written, ancient was spelled as AUNCIENT, okay? And you'll also see other, certain. So the way we spell it is CERTAIN, but it's spelled as CERTAINE, okay? So things like that. It's fun to actually look at different spellings that were used in those times. But let us get back to prime numbers. Okay, so here are some questions about primes. Okay, we can think about prime numbers in many ways. So what did early attempts to understand prime numbers look like? So there's at least two ways to view this question. Suppose I give you a very, very large number, okay, not just a 3 or a 4-digit number, but suppose I give you a 200-digit number, okay? Is there a way to determine whether this number is prime or not? Is there a method that you can use? And how long is this method? How much time does it take? Okay, another way to view questions about prime numbers is, instead of placing a particular number, suppose I place a huge table of numbers in front of you, okay? From that, is there a method that can teach you how to isolate all the prime numbers? Okay, so it's a method which will teach you how to actually get all the prime numbers in one go. Is there such a method? Okay. And then the third question is there a method to generate prime numbers as large as needed? Okay, so suppose you need, for some reason, for some application or for something, you need a very, very large prime number. Okay, say you need a 300-digit prime number. So is there a method to generate such a large prime number? Instead of you having to write all the numbers from 1 up till 10 to the 300 and, try to like locate what are the prime numbers, is there some way to just generate a very, very large prime number? Okay, and this last question is important for us today because it has an important application. Okay, so here is a very famous painting of Eratosthenes. This was made in 1635. Eratosthenes, of course, he lived much before that. Okay, and I'm going to tell you how he studied prime numbers. Okay, he was also a Greek scholar. Okay, so Eratosthenes gave us a very beautiful method to capture prime numbers. All right, so here is a table of numbers as a basic demonstration. Let us just take a table of numbers up to 100. Okay, and from this, what we want to do is we want to come up with a method that will tell us which are the prime numbers here. So how do we do this? So this can be done by a very simple observation. So Eratosthenes observed that if you have any composite, so a composite number is a number which is not a prime number. So what Eratosthenes does is he shifts your point of view and he actually first locates all the composite numbers. Okay, and then once you eliminate them, what are left behind are primes. So he observed that if you have a composite number n greater than 1, then it must have a prime factor which would be at most square root of n. Why is that so? Suppose you take a number n and you write it as a times b, where a and b are proper factors. Okay, then at least a or b must be less than or equal to square root of n, because if both a and b are strictly greater than square root of n, then a times b would be greater than n. Okay, but n is equal to ab. So any composite number must have a prime factor which is less than or equal to square root of n. This is the basic observation, right? Okay, so now Eratosthenes uses this to define prime numbers in a different way. He says that a number n is prime if and only if it is not divisible by any prime number between 2 and square root of n. So this is a somewhat inductive way of defining prime numbers. Okay, so in order to gather, so let's not get into definitions and stuff, but let us just see Eratosthenes, the observation of Eratosthenes in practice. So in order to gather all the prime numbers less than or equal to 100, we do the following. First, we locate those primes which are less than or equal to square root of 100. Now, square root of 100 is equal to 10, right? And what are the primes which are less than or equal to 10? These primes, so this, this much arithmetic we can just do by hand. So these are 2, 3, 5, and 7, right? Now what you do is, so first you pick 2 and you figure out what are the multiples of 2 in your table between 2 and 100. Okay, cross out those multiples since they have to be composite numbers. Okay, make sure you cross out the multiples, not 2 itself. Okay, next you take all the multiples of 3. What are the multiples of 3? 6, 9, 12, 15, 18, and so on. Okay, so and they come at regular intervals, so it's actually visually very easy to just eliminate them from your table. Then you cross out all multiples of 5, and finally you cross out all multiples of 7. Okay, once you cross out all these multiples, okay, What remain behind are the prime numbers up to 100. This is the idea of Eratosthenes. And this method is called a sieve. Okay, why is it called a sieve? I mean, it's something like you put all your numbers through a sieve. Those numbers which are composite numbers just fall out of the sieve. They are actually very, very refined. The sieve cannot keep them back. So they fall out. And what are left behind are the prime numbers. Okay. So if you look at this table of numbers, first in light green are the numbers 2, 3, 5, and 7. So these are the numbers, these are the prime numbers up to 10. Okay, then the numbers in pink are the multiples of each of these that you cross out one by one. And after all of that happens, the dark green numbers that are left behind are the prime numbers. And these are all the primes up to 100. And now, if you want to generate, if you want to come up with all the prime numbers up to 100 squared, namely that which is 10,000, you do the same thing with these primes you have determined. Take each of these primes and cross out all the multiples of each of these primes up to 10,000. Of course, this will take longer. As n becomes longer and longer, larger and larger, it will take you longer and longer to cross out all the multiples and isolate the prime numbers. Okay, so this is a very new method. And when it was introduced, it was a very fresh idea. Okay, and it helps you to view prime numbers in a slightly different manner. So what was the idea basically? The idea was that if you want to locate prime numbers, don't focus on the prime numbers, focus on composite numbers. Learn to eliminate the composite numbers, and what are left behind are the primes. Okay, so this is called the sieve of Eratosthenes. Now, from a computational point of view, this can take very long. Okay, as your n becomes larger and larger, this is still quite a long method. Okay, even though you may have computers, our computational powers are not enough to do this very efficiently. For example, if you choose a number n which has 200 digits, by the time our current computers will determine primality using the sieve of Eratosthenes, this planet will not be around. Okay, so it's just the amount of time required to perform this computation is just unbelievable. Okay, but whenever we learn a new method, we should not dismiss it because of its limitations. We should appreciate an idea for what it is. If an idea helps us to understand a concept in a manner which was different from what we'd studied before, that is a great thing to actually observe and learn. So Eratosthenes highlighted a new way to view primes. These are numbers which are not fine enough to escape through a sieve. And therefore, even though there are some computational limitations, you can build upon this idea and you can try to think of nicer methods or nicer sieves which can capture primes more efficiently. Okay, so here is a picture. Somebody made a painting of Eratosthenes in a very playful mood, sieving out the composite numbers. Okay. So now let us talk about collections of prime numbers. All right. Okay. So the method of Eratosthenes is somewhere around 200 BCE. And then starting then all the way till mid 17th centuries, there were several efforts made to record tables of prime numbers. Okay. So there was an English mathematician, John Pell, who lived from 1611 to 1685. He initiated a huge project to create prime number tables and factor tables as well. Okay, so he called his project a mathematical philosophical analog of the book catalog. Just like when you go to a library, there is a book catalog. He wanted to build a catalog of prime numbers. Now again, you may wonder why would you do such a thing? What is the use for it? But what he wanted, he was very committed to providing this resource to people who did mathematics. He thought, well, people may require prime factors or complete factor tables for each n. So as much as possible, I will try to give them this information. So today in class 10th, 11th onwards, you know, in your textbook, you are given log tables, like logarithms of several values of n, so that you don't have to keep calculating them. In a similar way, John Pell wanted to create prime tables and factor tables. And this was an interesting endeavor, and it went on. And under his instructions, a record of all prime numbers up to 100,000 was created. This can take very, very long. Okay, so as of 1668, we had a record of prime numbers up to 100,000. Okay. Then a German mathematician, there was a school in Germany that was also trying to do the same. So Carl Friedrich Hindenburg independently discovered the sieve of Eratosthenes, and he aimed at creating prime tables up to 5 million in the decade of the year 1760. And thus it was that a young 15-year-old person, okay, so he succeeded. Hindenburg, I guess until the year 1792, we had a record of all the prime numbers up to 3 million. Okay, so a young teenager, okay, who shares the first two words of his name are shared with Hindenburg, Carl Friedrich. So his full complete name was Johann Carl Friedrich Gauss. At that time, he was just 15 years old. He found himself staring at a table of all the numbers up to 3 million. Okay, and from those, he knew which are the prime numbers. That data had already been generated to him thanks to the efforts of very nice and kind people before him. And so he was able to just visually focus on the data and try to think of some pattern among the distribution of primes. Okay, now Gauss. Today he's called the Prince of Mathematics because he made many, many contributions to maths. Okay. So he lived from 1777 to 1855. This is obviously not a picture of his younger days. He was in his 60s by the time this portrait was painted. And this is a somewhat younger Gauss. He was around 50 years at this time. Okay, so as I said, he would go on to make many notable contributions to mathematics and physics, and it earned him the title, the Prince of Mathematics. Okay, by the time he turned 24, Gauss wrote a very, very important book. It is called Disquisitiones Arithmeticae. What does this book do? It is sort of like Euclid's Elements, but it focuses only on number theory. So this book lays out the conceptual foundations of number theory as a discipline in itself. And he was just 24 when he wrote this book. And it is in this book, actually, by the way, that the fundamental theorem of arithmetic about the unique factorization of numbers into its prime factors is stated explicitly for the first time. Okay, at the age of 15, he came across a table of prime numbers up to 3 million. And he made some observations based on what he saw in that table. He analyzed this data in batches and he made a conjecture. What is a conjecture? Roughly speaking, a conjecture is a guess. Okay, and then you have to check whether the guess is correct or not. Okay, so now this later on his conjecture was proved. So today it is given the name prime number theorem. But let us just try to understand what he conjectured. And please remember, he was just 15 years old when he did this. So pi of x, let pi of x, okay, so now we are not only learning Gauss's conjecture, we are also learning a language which helps us to express conjectures and mathematical facts in a nice way that people can appreciate and understand. So pi of x denotes the number of primes up to x. Okay, so what is pi of 2? Pi of 2 is just 1. Pi of 3, there are 2 primes up to 3, so pi of 3 is 2. What is pi of 4? Since 4 is not a prime and 2 and 3 are primes, so pi of 4 is equal to 2. And you can, for your, those of you who are watching, you can try and see what is pi of x for, let's say, all x up to 50. Okay, as an exercise, just see and see if it kind of shows you any patterns. And Gauss did this actually for all numbers up to 3 million. Okay, so as x takes in, what was his conjecture? As x takes increasingly larger values, the prime counting function pi of x, defined as the number of primes less than or equal to x, comes closer and closer to this value. Now, this value is not necessarily a natural number, whereas the prime counting function obviously is a natural number. But see how this is stated. We are saying it comes closer and closer to x over log x. What does that mean? More precisely, if you take the ratio of pi of x over x by log x, this ratio comes closer and closer to 1 as x becomes larger. Okay, now, so another mathematical language, a mathematical notation which is used to express this is that pi of x is asymptotic to x over log x as x goes to infinity. Okay, now let us just look at some numerical evidence. So here is, so I took this table from the Wikipedia page on prime numbers. Let's just observe what is going on. So here's this prime numbers up to 10, prime numbers up to 10 square, 10 cube, and all the powers up to 10 to the 17. Okay, so this is a much larger value than Gauss had access to. But you observe the number of primes up to 10 and the ratio pi of x over x by log x. We want this ratio to converge to 1 as x becomes larger and larger. And notice what is happening to this ratio. So you have 0.921, then 1.151, then you have 1.161. It seems to be growing, okay? It seems to be going away from 1. But then in the next stage, it comes closer to 1, 1.132, and so on. And as you keep going on and on, you will notice that this ratio, it is not hitting 1, but it is coming closer and closer to 1. Okay, so this is what, so this is numerical evidence in favor of Gauss's conjecture, but it is not a proof of the conjecture. So this conjecture was made in 1792, and it took more than 100 years to actually generate a complete proof. Okay, now at this time, I want to discuss the notion of elementary. Okay, when you see, an elementary problem, what does it actually mean? So in mathematics, the word elementary does not necessarily refer to the level of difficulty of a problem. Okay, instead, what it indicates is that the problem can be easily explained to an interested school student. So students like the ones who are watching this talk, all the things, all the different theorems, etc., that I have talked about until now can be stated in a way that you could understand, right? I hope you could understand. So when we use the word elementary, we are not referring to whether that particular question has an easy solution or not. We are only indicating that the problem can be stated in elementary terms. Sometimes it takes centuries of serious thought to discover any new insight on the problem. So what you do is, in fact, the field of number theory, this is a common issue that comes up. Young, eager students, okay, they watch talks on number theory. They get introduced to some problems which look elementary, and they start working on it. And that's a great thing to do. I mean, if you love math and you want to solve problems, hey, why not, right? But then you keep trying and you keep trying and you keep trying. Then you ask your teacher, and your teacher also keeps trying and trying and trying. And then lots of people get involved with that question, and they keep trying, and you're not really getting anywhere. And it takes centuries of serious thought to actually get anywhere with that problem. to solve it completely. So this could include, what happens is, many a times we are working on a problem with the tools and techniques that we have with us, but it's not taking us anywhere. So somebody has to come in and give us a fresh idea. Okay, that new idea or the new way of interpreting a problem is what eventually leads to a solution. Okay, and this new interpretation opens up the problem to strong techniques from other areas which you had not thought of using before. Pretty much these two aspects pretty much describe what research in mathematics means. Okay. All right. Okay, so the conjecture of Gauss. So all these things that we just said, in the context of the conjecture of Gauss, it gave birth to the discipline of what is called analytic number theory. This is a field that brings in sophisticated tools from calculus, so real analysis at school level, you call it calculus. And then you also have a field called complex analysis, which is basically calculus on the complex plane. Right? The calculus that you learn in school is calculus on subsets of the real numbers, intervals of real numbers, right? But for complex analysis, now you have the entire complex plane, and you learn the notions of differentiability and integrability there. So all this new thought, this new philosophy had to be brought in before Gauss's conjecture became a theorem, before it was proved completely. Okay, now let me just quickly, let me also tell you, so in case you thought that the statement of the prime number theorem was abstract, let me just show you the theorem in action. Okay, so again, now you'll see I'm obsessed with numbers with 200 digits. Okay, so what would you do if you needed a prime number, a really large one? Let's say a number with 200 digits, okay, or you can even go higher, 300 digits. Well, let's start with, suppose you need a prime number with 200 digits, okay? So what we do is, we consider the set of numbers, okay? So we have, and you don't, it doesn't exactly have to be 200 digits. If you give me a number with 199 digits, that will also be good if it's a prime. So what is the prime number theorem telling us? If we want to apply it in a computational way, let us take the set of all numbers up to n, where n is 10 raised to the 200. Okay? What does the prime number tell you? The probability that a number little n is prime is asymptotic, or it is close to, somewhere approximately equal to the number of primes divided by the number of numbers up to n. So number of primes is n, is asymptotic to n over log n, and the number of numbers is just n. So what the prime number theorem tells us is that for a number in this set that we have written, the probability that n is prime is close to something like this number 1 over 460. Okay. So in other words, if you think about this a little carefully, what this means is, suppose we perform an experiment in which we choose a random number in this big set. Okay, it must be chosen, like this number must be chosen randomly. You randomly place your hand on certain numbers. What the prime number theorem is telling you, that there is a very high possibility that within 460 experiments, okay, you will be able to locate a prime number. So if you choose the numbers truly in a random sense, whatever that means, we won't go too much into the technicality of that. But what the prime number theorem tells you is that 460 experiments are enough, would be most likely enough to give you a prime number in that range that you are looking for. Okay, so this is prime number theorem. Of course, this evolves into more sophisticated computational principles. What I told you was just a very, very watered down version. But this is to show that Gauss's conjecture Okay, it's not just something that is, very abstract of no use to us. There are many different ways of interpreting that conjecture, which later became a theorem, and this is one such way. Okay, now I want to move to France. So far, I've been telling you about developments in Germany. Now let's move to France and let's go back a couple of 100 years. So we have this young person, Pierre de Fermat. He was a lawyer. He was a lawyer who absolutely loved mathematics. So whatever free time he had, he would spend doing mathematics. So he lived from 1601 to 1665. And one of the things that France does really well is that they honor their scientists. They honor their scholars. Okay, they make these huge monuments in their honor. And anywhere in France you go, you will see some nice monument dedicated to some big scientist who came from France. So this is a monument dedicated to Fermat. So now what did Fermat do? So Fermat also made many, many contributions to mathematics. In particular, there is a theorem which is often called Fermat's little theorem, which in fact, it leads to this safe method of transferring money that I told you about. So Pierre de Fermat was a French lawyer, and he made some discoveries about prime numbers, which today have significant real-world consequences. So what is his theorem? So by the way, I must tell you that he did not actually prove this theorem. He made a guess. So this is also a conjecture that he made, and he wrote to some friends about it. And this conjecture was actually proved more than 100 years later. So what does it say? It says, well, let P be a prime number, all right? And let A be any natural number, not necessarily prime, but it should be co-prime to P. So you start with a prime number, and then you take a natural number A, which does not have any factor common with P other than 1, okay? For example, 3 and 6 are not co-prime because they have a common factor of 3 in both numbers. But 3 and 23, okay? Or 3 and 22, okay? Those are co-prime numbers. So you start with the prime number P, and you take a natural number which is co-prime to P, okay? Then Fermat's observation was that whatever this number is, you take A, raise it to P minus 1, and from that power, you deduct 1. Whatever that number is, it has to be a multiple of P. How would you even guess something like this? So he was, of course, working on many questions, and he was doing a lot of experiments. And this was an intelligent guess he made based on what he was looking at that point of time. And this little theorem, now it's called Fermat's little theorem, has plenty of applications. Okay, now, by the way, so here is something for you to think about. If you have a prime number P, any number which is less than P will have to be co-prime to it, right? Because by definition, a prime number does not have any factors other than P or itself. So if you take a number 23, for example, and you take any number which is less than 23, say 21, 20, 19, they will all be co-prime to 23, all right? So in particular, we may take some natural number A, which lies between 1 and P minus 1. Or you could also take a natural number A, which is greater than P. Just make sure that it is not a multiple of P, okay? It must be co-prime to P. So the other thing is, why is it so important for A and P to be co-prime to each other? Well, let us take two numbers A and P, which have some common factor which is greater than 1. Okay, because of the fact that P is a prime which does not have any proper factors, if A and P have a common factor, that factor has to be P. It cannot be some proper number less than P. Okay, so P divides A. What that means is that P must divide a power of A as well. It must divide A raised to the P minus 1. Okay, and if it divides A raised to the P minus 1, and you deduct 1 from this number, it cannot possibly be a multiple of p. Why so? Well, here is an exercise for you. If p divides a number n and it divides a number m, it must divide n plus m, or it must divide n minus m. So here in this case, if you had p dividing a to the p minus 1, and you also had p dividing a to the p minus 1 minus 1, then it must divide 1, which is obviously garbage, right? Because you are taking p to be something greater than 1. How can it divide 1? Okay, so it is important for us to take a natural number which is co-prime to p. It should not be a multiple of p. Okay, here this is where you bring out your notebook, or if you want to use a calculator, be my guest, do so. Let's do some examples of Fermat's little theorem. Okay, so let us take the prime number p equal to 2. And let us take a to be equal to 3. Okay, then 3 raised to the 2 minus 1 is 3 raised to the 1, which is 3, minus 1 is 2. And 2 is obviously, it is equal to 2, therefore it is divisible by 2. So this is an example of Fermat's little theorem in action. Let us take some number which is not a prime. Okay, and let's check whether Fermat's little theorem holds for that or not. So let n equal to 6 and let a be equal to 5. So choose a which is co-prime to your n, but choose n which is not necessarily a prime. So n is equal to 6 here and a is equal to 5. Okay, so what is 5 raised to the 6 minus 1 minus 1? So 5 raised to the 5 minus 1. Okay, so 5 raised to the 5, you can verify is 3125. And when you deduct 1 from it, you just get 3124. And you can check that this is actually not divisible by 6. Okay, so Fermat's little theorem seems to fail for numbers which are not prime. Let us take a slightly larger prime. You'll see, even though the primes that we are taking are increasing by small amounts, the kind of numbers required to verify Fermat's little theorem just become larger and larger. Okay, so now you have a, which is 5, raised to the 7 minus 1, which is 6. You deduct 1 from it. Okay, go ahead, use a calculator. You get 15624. Okay, use a calculator again and verify that this is indeed divisible by 7. Okay, so P is a prime. So your Fermat's little theorem, we've seen a demonstration for the prime 7. Now again, let us take n equal to 8 and check whether, you can take various types of numbers and check if there are non-prime numbers for which Fermat's little theorem holds or not. I'm only going to give you a few examples. So n is equal to 8 and let us take a to be 11. Okay, the key thing being that 8 and 11 are co-prime. Okay, but 11 raised to the 8 minus 1 is not divisible by 8. All right, so far your calculator will be useful to you, even if you're using the calculator on your computer from which, on the device from which you are watching. Okay, so far the calculator will do, but if you increase the number primes to say 2-digit numbers, then the numbers just become very high and your calculator does not have the computational power to give you this answer. Okay, so you need computers with higher power, but Fermat's little theorem is telling you that even though you cannot actually sit and compute this number immediately, 82 raised to the 83 minus 1, which is 82 raised to the 82, and from that you have to subtract 1. Fermat's little theorem tells you that, well, calculator or no calculator, this number is divisible by 83. Okay, so that is the power of a theorem. Once you prove a theorem, then you don't have to verify the theorem for individual cases. A theorem tells you something, it tells you the conditions under which some statement is true. And then you just keep applying that theorem. Okay, now it turns out that the prime number theorem, along with Fermat's little theorem, they are both very beautiful topics and they sort of developed independently of each other, right? So one developed in France in the 1640s, and then prime number theorem started with this observation made by this 15-year-old German teenager. Okay, but it so happens that over the years, these two beautiful facts, these two very different looking ideas, they sort of meet each other and give us applications which are very important for the world today. Okay, so at this point, I will not be going into too much details, but I want to tell you some very interesting principles. Okay, so as I said, for several types of applications, today we require large primes. Okay, not just 200-digit primes, we require, 300-digit primes and so on. Therefore, these are huge numbers we are talking about. So we are always in search of methods that test the primality of large numbers in an efficient manner. So a combination of the prime number theorem. So the prime number theorem in action told us that you can perform a certain number of experiments, which is not high, and in very high likelihood, that will give you a prime number. Okay, but to perform each experiment, you need an efficient method to check whether a number is prime or not. So a combination of these two ideas will help us find large primes in a reasonable amount of time. So it just happens that Fermat's little theorem, over the years, the way the study of this little theorem developed, we saw that it ended up serving as a seed for several types of primality tests, including one very important contribution that came from India. And I'm going to tell you very soon about it. Before that, I want to mention a contribution, an application of Fermat's little theorem in the years 1976 and 1980, which led to a method for primality testing, which is actually used in most real world applications today. It has found many applications in e-commerce, for example. Okay, now I want to tell you a very beautiful contribution about this subject that came from India. It came from Indian Institute of Technology, Kanpur. So sometime in August 2002, so nearly 2 decades ago, there were 3 computer scientists at IIT Kanpur, Manindra Agrawal, Neeraj Kayal, and Nitin Saxena. They announced an article named Primes Isn't P. What does this title actually mean? I'm going to tell you that very soon. So Manindra Agrawal was a faculty member in the Department of Computer Science, and Neeraj Kayal and Nitin Saxena were his students. Okay, and they did a summer project, actually not summer, they did an honors project under him, where they started investigating some questions about prime numbers. And, although these were very, very young students, okay, along with Professor Agrawal, they proved a very nice, they came up with a very nice method to test primality of a number. Okay, I'm going to tell you more about it. Here are some technical words I'm using. Even though you may not have heard these words before, the whole idea of going to a talk is learning some new things, right? And also learning some new terminology, some new some new words. So what they obtained is called, it was the very first deterministic, unconditional, polynomial time algorithm for primality testing. This is their primality testing algorithm. What does it do? So what do these fancy words mean? I hope you are not too intimidated. You don't need to learn all the technical details, but basically, what is the strength of their method? First of all, that it certifies whether a number n is prime in polynomial time. Now, what do I mean by polynomial time? I'll actually tell you in the next slide. But essentially, it means that it checks the primality of numbers very efficiently. Next, it returns a definite and correct yes or no after a finite number of steps. This is the explanation of deterministic. Okay, so sometimes you have methods which don't give you a definite answer, but you know that as you perform more and more steps and get certain conclusions, the probability that a number is prime just becomes higher and higher. Those are called probabilistic algorithms or probabilistic methods. But one of the beautiful aspects of this particular algorithm is that it is deterministic. It returns a definite answer after a finite number of steps. And this finite number of steps is not very high. Third, and this is very important, is that it does not assume any unknown conjectures. Okay, all the facts that are used in their methods have been proved before. They are established certified theorems. All right. So this is the strength of their primality testing algorithm. I will not tell you about it. It's beyond the scope of this lecture. Okay, but I do want to explain this word polynomial time. It's quite fun to watch this in action. What does it mean when you say that an algorithm is, or a method is, a polynomial time method? So any method which requires that the number of steps to fulfill that method is some positive power of n, it will become quite inefficient as n grows. So even if you take a very small power, let's take n raised to the 1 over, say, so this is what, 10 raised to the 7, n raised to the 1 over 10 to the 7. Okay, when you take n equal to 10 to the 14 or 10 to the 26 and so on, okay, the number of steps also becomes very, very high. So if you have a method where the number of steps is some power of n, that is an inefficient method. On the other hand, if you have a method where the number of steps is approximately around the logarithm of n, okay, then that method is quite efficient. So why is that so? Log n grows very slowly in comparison with n raised to the a, for any a, however small. For example, suppose I take n to be equal to this massive, huge number. So it's not, we are not even talking about 200 digits anymore. We are talking about a number which has at least 10 to the 14. In fact, it has exactly 10 to the 14 digits. Okay, so we see that if you raise, so you take this number, this humongous, this huge number n, and raise it to the power 1 over 10 to the 7, you end up getting another huge number. It is smaller than n, but it is still quite a huge number. But what happens when you take logarithm of n? Log of n is 10 to the 14 times log 10. Okay, and therefore, so now you have log 10 is quite small, it's not very big, and then you have 10 to the 14, right? So obviously, 14 is a much smaller number than 10 to the 7, right? So 10 to the 14 times log 10 is much smaller than 10 to the 10 to the 7. So this is the advantage of having logarithm. Any logarithm of any n is substantially smaller than n raised to the a, however small your a may be. Okay, as n becomes very, very large, log n will always perform better. Okay, so you can take log n, or you could have powers of log n whole square, log n to the cube. Okay, those would any day perform better than n cube or n to the a for some small a. So a polynomial time algorithm is a method which can be performed in a certain number of steps where that number is roughly to the order of log n or some power of log n. Okay, so it's an algorithm in which the number of steps is something to the order of log n raised to the c, where c is some absolute positive constant. You don't want log n raised to the n, okay, where n keeps increasing, this number of steps will also keep increasing. So c is some positive absolute constant. And to say that primes is in P, which was the title of the paper of Agrawal, Kayal, Saxena, is to say that the primality of n can be checked in approximately log n raised to the c steps. And the value of c that they had was 7.5. Okay, so log n raised to the 7.5, okay, roughly to that order, that is the number of steps required to check whether a very large number is prime or not. Okay. The amazing thing about this algorithm is that it is built on very simple principles. It uses a generalization of Fermat's little theorem. And today, I mean, this work is certainly counted among the most important mathematical discoveries in recent times. It's a very, very big contribution to the study of primality testing. And it is very inspiring that it came out of an undergraduate research project. So it was two college students essentially working with the professor, and they learned, not only did they learn something new, they were able to solve a very important mathematical problem using very simple techniques. Many people had attempted to prove what they proved, but they were using somehow, people had started using very sophisticated arguments, and it was leading them nowhere. So a new, fresh, original insight came, and this led to a solution of the problem. Okay, so here is a nice cartoon that appeared soon after. So this algorithm is called the AKS algorithm. So this is a cartoon by Larry Gonick. You should check on Amazon. Larry Gonick is a cartoonist, and he's also written several books explaining mathematical principles with the help of comics and cartoons. Okay, so 7.5 logs should do it, is what Professor Manindra Agrawal in this picture seems to be saying. Okay, so now before finishing, I want to quickly tell you, quickly go back to the application that I had promised to tell you about. But so here are these 3 important computational principles. So the study of prime numbers tells us 3 important facts. What are they? First, it is easy to generate large potential primes. Next, it is easy to decide whether a large number is indeed prime. So the first, by the way, is done with the help of prime number theorem and other sophisticated versions of the prime number theorem. Then it is easy to decide whether a large number is indeed prime. Third, this is extremely important for us. It is extremely difficult for a computer to factor a large number. And we are talking about really large numbers here. Okay, so what does easy mean? It means that the work can be accomplished by a computer in a reasonable time. Okay, but difficult means the opposite, that it can take unbelievably long, or it take the kind of time taken by the computer to factor a number is not the kind of time that we have. Okay, we need to do that thing much faster. So these 3 facts combine to give us, as Mr. Bachchan puts it, a safe method, hassle-free method and quick method to exchange sensitive information on online platforms between valid parties, okay, without being hacked by an unauthorized third party. Okay, and again, Fermat's little theorem plays a very crucial role in this method. All right, so now I'll have to go over slightly quickly on this, but to indicate the main principles. So what does Fermat's little theorem tell you? Do I have a few more minutes?
Yeah, maybe 5 more minutes.
Yes, I'll finish within 5 minutes. Okay, so let's. So you have Fermat's little theorem, okay, which tells you that a raised to the p minus 1 is divisible by p. Okay, there is actually a generalization. Okay, so I'm going to. It becomes a little more technical here, so we will not worry too much about the technical points. But I do want to run over the method, tell you how it is applied. Okay, and then you you learn how ideas can grow and develop over several centuries. So here is so like I said, Fermat's little theorem was not proved by him. It was proved nearly 100 years later by another very famous mathematician called Leonhard Euler. Okay, so Leonhard Euler in fact proved a generalized version where he took not just primes, but numbers which are products of primes. So these are called semi-primes. Any number which can be written as a product of 2 distinct primes is a semi-prime. So in that case, the generalization of Fermat's little theorem is that this semi-prime p times q must divide this particular power subtracted by a. And this beautiful principle was used, notice the time, 240 years later, 3 computer scientists at MIT in USA used this principle to develop a method to share information between 2 parties safely. Okay, now let us just understand how information is exchanged. suppose you are a spy working for an organization, and you have a friend spy who is, say, posted to some other country working for the same organization, and you want to exchange information among yourselves. Okay, because that person is your friend, you know them beforehand, you have already developed a secret method by which you will share information with each other, and you'll hope that no third party will know how to actually decipher that message. Okay, but in most applications in real life, it is not possible to decide this privately beforehand. When a bank gives you a credit card, your credit card number is a very secret number, right? Your bank official is not going to call each of you personally and tell you, hey, this is a secret code and this is how you're going to, disguise your message, and then I'm going to decrypt it. It does not happen like that. What the bank does is it makes the encryption method public. Okay, so that any software, when you go to the bank's website and you put in your credit card number, it is able to disguise or encrypt the message quickly. Okay, so this method is made public. Okay, so the encryption key is made public. So the RSA method, named after the three creators from MIT, the idea is that the key to encrypt a message is made public. So anyone can encrypt a message, sign it, send it across, but only the intended receiver has the knowledge to decrypt a message. Okay, and deduce whether it comes from a genuine sender. Okay, so this Fermat's little theorem and its generalization helps you to do that. Okay, so I won't go too much into it. Let's just go over this. Okay, but let's learn some very beautiful facts about the RSA algorithm. So this RSA algorithm was first announced in 1978. Okay, the authors estimated that according to the computing resources of those days, if you had a number with 100 decimal digits, okay, and you wanted to factorize the number, it would take this many years to actually factor a number. It's a huge number of years. We don't want to do that. Okay. Today, we have more sophisticated computing resources and methods to factor numbers of this size. So we can go to numbers of even bigger size, 200 decimal digits, or 232 decimal digits. So these methods to factor numbers now originate from far more sophisticated tools, okay, which are called the number field sieve. The seed of the number field sieve is, of course, the sieve of Eratosthenes. And then there is another beautiful topic called elliptic curves, etc. So these methods, they are now becoming increasingly sophisticated. Okay, and we use very large numbers for encryption with factoring times which are unfeasible. They're very, very long using current technology. Okay, so now let me show you something fun. Go to the web page of your favorite bank. Okay, let's say you go to State Bank of India. All right. Next to State Bank of India, if the bank web page is a secure web page, there will be a lock. Okay, there will be the symbol. You click on this lock. Then it will give you it'll either tell you that, yeah, this is a safe site, you can trust it, click OK. Or if you want to know more details, you click on Show Certificate. Okay, I hope some of you will do it with me. Go to any favorite bank of yours. Okay, when you click on Show Certificate, you get some more information. Okay, click on Details. And when you click on Details, it tells you the method which is used to encrypt and decrypt your bank information so that it remains same. So when you're doing a transaction with your bank online, the third party will not be able to hack. So this is the method that they use to sort of keep to keep your transfer of information safe. And you will see the algorithm they are using is a version of the basic algorithm I wanted to tell you about. So it is the RSA encryption method. Now, of course, over years, it has become very, very sophisticated. So there are many different parameters that we have to see. But basically what this site is basically telling you is, it is announcing publicly the encryption key, but it is not announcing the decryption key. Only the bank has that. And if a third party tries to decipher the decryption key, it will take them like millions and millions of years, okay? So do go to your favorite, even you don't even have to go to a bank website. You can go to Facebook, or you can go to your favorite social media site, which is secure. Anything that requires a login, click on the lock and see what method they use for encryption. And you will see most of them use RSA encryption, which was first announced in 1978. And the fundamental tool in the RSA encryption was this beautiful theorem of Fermat in the year 1640. So I now want to conclude my talk by giving you some things to reflect upon. Okay, so the joy, what is, we are all here to discover things and, find joy in it. So what this story tells us is that Fermat and many other people, they were purely driven by the joy behind their study and their discoveries. They loved numbers, or they loved whatever part of maths or science they had, and they really pursued it due to pure joy. They were not worried about applications. They were like, okay, I love this, this makes me curious, I want to investigate. So they did that. Sorry? Yeah, I'm about to finish. Yeah. This is something I really want the students to hear. So each mathematician built upon the work of another person. Okay, so after Fermat, other people came, including the Agrawal-Kayal-Saxena algorithm I told you about. They built upon the work of Fermat. So this building upon can take centuries and centuries. It is an ever-continuing process. Everyone had a fresh way to look at things. Everyone had a new idea. This idea led to the development of the subject. But at the heart of it, their motivation was just to have a better understanding of what they wanted to study. The application and the way we use it in our modern world today is a byproduct that came more than 350 years down the line. But Fermat was not worried about, okay, 350 years down the line, is there going to be an application of this? No, he just asked a question about prime numbers and he investigated the question. And he also shared his question with many other people. So lack of immediate applicability should not hold back our study. We should just pursue our study for the joy of study. And always remember that the pursuit of knowledge is full of pleasant surprises. And today we may not know what our ideas will mean to the people who will come in the generations after us. But we should just honestly pursue our study and learn new ideas, and also make an effort to communicate them widely. Okay, so I hope you can reflect upon these things, and it is time I stop my lecture.
Thank you, Kaneenika, for the energetic talk. We learned a lot of things from your talk, but I guess this last slide, at least in my opinion, is perhaps the most important slide. We do what we do because we like it, for our pleasure, but some of these things that are created maybe 50 years or several hundreds of years down the line find applications. I think there are questions on YouTube, but unfortunately we don't have any further time today. I'm sorry about that.
Yeah.
Sorry to hurry you up. There is a talk at 6 o'clock, which is going to be live streamed as well. So consequently, I think it's 3 minutes to 6 o'clock. Let's see whether we can take 1 or 2 questions.
Sure. I see a couple of interesting questions, and my talk also addressed them. Can I take those, or would you like to tell me which ones to take?
No, you take one.
Yeah. Okay, so Sajna Hamid is asking, I would like to know how these numbers are applicable in real life. So Sajna, I just told you that they are used. I gave you one specific application to safe transition of information from between a bank and a user. So it's a very important application. We cannot imagine a digital life today without prime numbers. Okay, then Harshi asks, can we find primes for numbers larger than infinity? What do you mean by larger than infinity? Okay, so I guess what you want to know is, can we find prime numbers which are very, very large? Okay, and yes, we can. This is something that is relatively easy. We can find primes with very, very large numbers in a relatively efficient time. Then somebody has asked, each website has its own encryption algorithm? Yes, it does. The basic method would probably go back to the RSA encryption method, but the parameters that they use could possibly be different.
I think we have to stop there.
Sure.
Okay. Thank you very much again, Kaneenika, for agreeing to deliver the talk, doing the needful and enlightening young students with your insights. We'll close this session.
Thank you for having me.
Vaishnavi, you can present.
Thank you so much. Thank you so much, Kaneenika, for that journey through time and space all over the world, enjoying the joy of discovery and showing us the secrets of primes. Do we have time, a couple of minutes before the next session?
Yeah, 2-3 minutes you can quickly present.
Sure. So, a couple of quick announcements about the Science Week. Thank you all for joining us today for this very enlightening session. We have several more upcoming talks over the course of the next few days. Right now at 6 p.m., we have a very exciting talk by Professor Pradeep of Department of Chemistry, IIT Madras. The topic is Science, Technology and Innovation for Sustainable Clean Water. And the link has already been shared in YouTube chat. So we welcome all of you to join us there. We have a couple more talks for teachers, how to bring out the joy of science in class and how to bring out the joy of maths in class, presented by S2S Education. We also have a very exciting talk by Professor Rohini Godbole from Center of High Energy Physics, IISc. This talk will be about the heart of matter to the edge of the universe, and this talk is on Saturday, March 5th. And we'll be concluding Science Week with a very exciting talk for students to discover the magic of maths through paper folding by Dr. Ashwin Guha from Seed2Sapling Education. Couple more quick announcements from S2S. We have a very exciting contest for all of you students, teachers, and all science and maths enthusiasts. We'll be organizing a contest, a very unique contest to ask questions and share your observations. So oftentimes we find that there are contests for quizzes and projects and so on, but here we are sharing a contest specifically for asking questions to encourage that curiosity and encourage the process of discovery. So this contest will launch right after Science Week, and it will go on till March 20th. Please stay tuned and join us for future sessions to learn more about this contest. We also have a very exciting program, the Joy of Learning program. This is a program for all the teachers. We'll have two separate courses running for the science and maths teachers. It'll be a 12-week course, and you will receive a certificate from the Academy Trust. All the details will be shared once the Science Week is over. During this course, we will be exploring a lot more ideas and means to implement the joy of learning in class. We all have the constraints of, aligning to syllabus and curriculum. We have constraints of time, and oftentimes we don't always have the time to experience the joy. So we will engage in a lot of dialogue and work on, bringing back that component of joy in the classroom. Stay tuned for future sessions to learn more about JOL and how to register. So I think we're getting late now for the next session. Please join us and the link posted on YouTube to the next session. Thank you all very much. Thank you again, Dr. Kaneenika, for the engrossing talk.
Thank you very much. Bye.
Thank you, Kaneenika.
Thank you. Bye.
Bye.